In this video, we present building rearticulable models for arbitrary 3D objects from 4D point clouds. Given a short point cloud sequence of arbitrary articulated objects, the goal is to output an animatable 3D model by discovering distinct object parts, inferring which parts are connected, and the joint properties between each connected part pair. Articulated objects composed of more than one rigid parts connected by one-off joints. Each joint is either a bevel joint or a prismatic joint. A large body of work tackled this problem in a category-specific manner, but doing this for each new category requires manual effort and can't scale to arbitrary objects and novel classes. Recent works also proposed category-agnostic modeling. However, those methods are limited to only infer a single joint or fail to reason the kinematic tree or without taking one-off nature of the joint into consideration. In contrast, our work simultaneously achieves all three requirements, inferring parts, kinematic connectivity, and joint constraints. The kinematic model comprises of n parts. Each part is connected to its parent part. We use a coordinate-based semantic field fx to parameterize the part segmentation at a canonical time step. Each joint is parameterized by screw parameters, specifying the joint location and axis. The articulation is controlled by a set of joint state parameters, where each joint parameter represents the rotation angle or translation along its axis for joint I at time step t. We estimate articulation model parameters by energy minimization. The energy measures the compatibility between the articulated point cloud according to the inferred model and observation at each step, which contains both geometric and motion terms. However, directly optimizing over the set of model parameters is difficult, as it involves both discrete and continuous optimization variables and structured constraints. To this end, we pursue an alternate relax and project approach. Our method first feeds a relaxed model without constraints. Then, in the projection stage, we cast the solution to a valid kinematic tree by measuring spatial proximity and one-off constraint. Finally, we fine-tune estimated model parameters. Here is an illustration of optimization procedure. In relaxation stage, the model doesn't constrain the parts to form a kinematic tree, and lets individual parts to follow their own independent 6-law trajectory over time. The estimated relaxed model parameters are projected onto a valid kinematic tree so that each joint follows one-off constraint. We further optimize the model over the original problem. Here, we show our first experiment on robots. For each robot, we show input sequence on the left, animatable model in the middle, and reanimation results on the right. The animatable model includes part segmentation, kinematic topology, and implied flow using our inferred model. Our method works well on all kinds of robots, including humanoids, quadrupeds, mobile manipulators, arms, and robotic hands. Next, we show qualitative comparison against multi-body sync and watch and move. Multi-body sync sets up a joint synchronization problem to obtain a temporally consistent part segmentation. However, it requires accurate pairwise flow predictions and does not work well in longer time steps. As a result, multi-body sync tends to undersegment the point cloud and generates oversimplified topology. Watch and move uses ellipsoid primitive represented by sine distance function to build articulable models. The method uses soft assignment of points to primitives and does not incorporate the one-off constraint of articulated objects. This leads to incorrect assignment of points to parts and overcomplicated results. Then we show results on daily articulated objects. For each object, we show input sequence on the left, animatable model in the middle, and reanimation results on the right. The input sequence is not aligned, thus all frames have different global poses. The inferred one-off joint are shown in red, and reanimation results have 4 time steps. Our method works well across objects with different number of parts, different kinematic structure. Our method also works well on different types of articulations. Our method could recover both the revolute and prismatic joint in the furniture. Finally, we verified our method on real-world scans with diverse articulations and kinematic structures. The scans are gathered using scan apps on iPhone. Our method could successfully recover the revolute joint of the toy. It also works well on a switch with two prismatic joints. Our method is robust to noise and partial observations. Thanks for watching.